For this problem, remember, you've got this written in as a structural formula. So use that to your advantage. Let that help you with your chunking to figure out what your central atoms will be. Now over here, you're going to have a little bit of logic you're going to have to think through. So recognize the pieces that are really common, and then figure out how it's all going to fit together. Go ahead and pause the video and give this a try, and then unpause and we'll talk through it. Okay, now this problem definitely has a bit of a challenge to it. So let's go ahead and work through it. We know that we're going to have our CH3 group. We have CH3. Now, what I'm going to do is I'm just going to talk through it using our shortcutted way of knowing how many bonds things usually have, and kind of treating it like little puzzle pieces that we put together. That's the really fast way to draw most of the organic molecules. That's a fast way to handle it. And remember, organics are ones that are based mainly on carbon and hydrogen, and may have oxygens in them as well. And sometimes some other substituents, some other groups on the periphery, some other atoms. But most of it's going to be carbons and hydrogens and oxygens. Now we could also do that by thinking through all of our valence electrons, and we get the exact same result, but it takes a lot longer. So try to polish this approach and be able to do this too. So we have our CH3 group. Then notice I point out we have a carbon here as our next atom. We don't know for sure what's happening with the oxygen yet, but we know there's going to be a CH3 group somewhere. We know that CH3 is going to be an entire piece, but you need a fourth bond on carbon. Oxygen is going to have two bonds. So if I had done it like this, I'll just compact it for a moment. Notice that we're still going to end up being too short on this carbon. So that's not going to work. Let me go ahead and erase that approach. Instead, what we're going to want to do, we know the oxygen is allowed to have two bonds. So it can also stick off of the side of here. Then we can put the CH3 out here. Carbon has 4 bonds like it should. Oxygen has 2 like it should. Each of these has what they should. Now we can say, okay, on this very quick way of handling it, we should be able to expect that this is a real molecule. And this is what the structure should be for our Lewis structure. Now, if you didn't get that, and you wanted to work through it again, now would be a good time to just restart the video and work forward to this point. If that part's a little bit confusing for you, but you're confident enough that you'll get it later, you can continue to go forward and focus on the three-dimensional structure. Or if you got all of it, then we're in really good shape so far. But make sure, no matter which of those options you're in, make sure that you polish this enough that you can do this entire problem eventually on your own, and eventually should be on a very short time scale. It should be pretty soon that you can handle this totally on your own and get the correct answer. So, if you need to, go ahead and pause. Okay, now what we're going to do is we're going to go through the three-dimensional structure for each of these. We need to end up with our EXE notation for each of these 3 atomic centers. Here I've got my central atom, as always. I've got 4 bonded electrons, AX4, no electron pairs. It'll be an AX4 geometry. This has a total of 3 atoms attached to it. So it'll be AX3, no electron pairs, so AX3 is the final geometry for it. And then here I've got the same thing as on the previous end. So it'll be a AX4. So I have my geometries for each of those assigned now. Both my electron group and my molecular will be the same, since there's no electron pairs to worry about. So, I know that this part is going to be tetrahedral. I know this is going to be trigonal planar. And this one's going to be tetrahedral as well. So what we want to do is we want to think through what we need to do in order to make the drawing as simple as possible. Let's start with the central atom then, because this is all going to be in the same plane. So if I draw my C, double bond to O, then my single bond's coming off of that. I know it's trigonal planar. These will all be in the same plane. I can go ahead and put my carbons in right down here. Now I know that typically I'm going to have my hydrogen that's in the plane be on the opposite side. We can rotate it and have it other ways, but that's an easy way to draw it. That means that my wedge bond and my dash bond, in other words my forward and my backward, will be pointing the opposite direction. Now we stick our hydrogens in at the end. So that's what this should look like. Then I'd say, okay, I've got my double bond right here, which means it should deviate things a little bit. So this area right here should be just a little bit less than 120 degrees. And these should all be at 109 degrees, 109.5 degrees. And that's because carbon and hydrogens, they don't really deviate very much. You know, we don't have anything terribly lopsided. The carbon isn't so much bigger that it matters. So we'd expect these to be about 109.5 degrees. This is the only spot that should deviate by much. And so if we really cared to, we could give it another redraw where we squeeze this angle down just a little bit. But realistically speaking, we can just label it as less than 120 and move about our business. So that's the end of our problem for this one.